My project is in situ resource utilization of Martian Regolith for construction year 4. In situ resource utilization means using what's already available in situ or in that place, as it would be costly and inefficient to have to shuttle materials from Earth to Mars. I've done my research on sulfur concrete. Regular concrete is made with aggregate, water, and cement, but water is a valuable resource on Mars, and cement isn't available as it's made with limestone. However, sulfur concrete is composed of aggregate, in this case the soil or regolith, and sulfur, which is available on Mars, heated and mixed together. Additionally, regular concrete takes about 28 days to set and even longer to reach full strength, but sulfur concrete is at full strength immediately after cooling. There have been many studies on the applications of sulfur concrete for the Moon and Mars. There was a study in the 1990s sponsored by NASA that looked into lunar sulfur concrete, and various studies followed, but only recently did a group from Northwestern look into Martian sulfur concrete using a Martian soil simulant, and they found an optimal ratio of 50-50 sulfur to aggregate. Additionally, there's a lot of potential on Earth because there's a lot of excess waste of sulfur coming from the oil and gas industries, and there are low water areas. In the past, I've studied how best to make sulfur concrete, like here with a hot plate and ingot mold, which I eventually developed into an oven and silicone. And I also changed different aggregates and different iron just to be able to see what's strongest. And I did get to test with a universal testing machine at a lab at UCF, which helped me figure out that the compressive strength of sulfur concrete is actually just as strong as high strength Portland concrete. So I decided to ask, how can we actually use this sulfur concrete to build on Mars? And I decided on additive manufacturing, which is basically 3D printing material layer by layer. And there are actually some companies on Earth that are currently doing this. Like you see up here, this is Core, and they are actually 3D printing buildings using concrete on Earth. So I designed a system for additive manufacturing on Mars, which I call SAMM. And this is the picture from last year of the whole system. But this year I wanted to create a new and improved extrusion system. As you can see, this is the extrusion system from last year. On Mars, there is lower temperatures and a different gravity. So ultimately there would need to be heated tubing and some sort of pumping system, as opposed to last year's when I was totally just relying on gravity. And I even had to run through hot water just to get it hot enough to be able to flow. So this year I wanted to add in heated tubing, a heated reservoir, and a peristaltic pump. So when I was trying to decide on that pumping system, air compression I had tried last year and it failed. Hydraulics uses water, which kind of defeats the point of sulfur concrete. Gravity is different on Mars, and it kind of lacks a bit of control and precision when it comes to actually controlling that extrusion ultimately. So I decided on peristaltic pumping when I remembered peristalsis, which is a biological term that refers to the squeezing motion that's used in the digestive tract to force through food. And peristaltic pumps are actually a really common standard thing. They're really popular because they're able to keep things from becoming contaminated because they keep material and tubing separate from equipment. And they're able to essentially squeeze through using pressure and vacuums. They're able to squeeze through really viscous liquids and even solids. So my methodology was in a series of stages, and I first started out just testing with gravity like last year, but adding in those heating elements. Then I made the pump and the extrusion system, and then I started pumping through water, then pumped through sulfur concrete, and then put it all together with the gantry system from last year to actually extrude it in a shape. So this is the overall system flow diagram. As you can see here, the first part is making the sulfur concrete. It takes about 90 minutes per batch. And then I could put it in the reservoir, pump it to the system, extrude it from the gantry cart, which is attached to the rest of the system that I control with my laptop. And now there are a series of trials of developing it. There are 13 in total. At first, I started at stage 0, just trying to get it to pump through just using gravity. But I added in that reservoir and that tubing, so no hot water this time. And I put it in, but it immediately got clogged right here in that nozzle. So I rearranged it, had it go straight down to start. This time the nozzle was not clogged. However, it wasn't pumped through. The sulfur concrete, it remained in that molten usable state in the reservoir, but it was just too thick to be pulled through. And that really just showed me the importance of having some sort of pumping system as opposed to just gravity, especially with thicker, more optimal ratios. So then I moved along, I created the peristaltic pump, I created the extrusion system, even though both those stages are extremely iterative in this process, but this is the first design of the pump trying to pump through water. And this is a triangle rotor with 3 different wheels. This was not successful, and I noticed that that triangle shape had kind of distorted the tubing, so I switched to a square. This was also not successful. Wasn't really sure what was happening, so I did a little bit more research, and I decided that it was probably because the tubing was not being compressed enough. So I wanted to create more of that vacuum seal. So I went to a 3.3-inch square. This was able to successfully pump through the water. Unfortunately, it also pumped through the tubing. It started to move through the system and totally mess it up, which was not good. So I determined that that was actually too tight. So I went to 3.15 inches. And this time I attached it to that tape and the reservoir. However, this was really wobbly. So I decided to remake that rotor with a drill guide to try to keep the hole more centered. And I also used a hex screw instead of a bolt so I could easily attach with the drill I was using to power it. And I made a few more attachment adjustments that made it a really stable system, was able to pump through water, and I decided it's time to move on to stage 4 using sulfur-concrete. However, almost immediately, the pump came totally out of place because the tube clamps that I had been using were made of plastic and got melted through by the tape. So I replaced them with metal, and this time I eliminated the tape from inside the pan because I was trying to eliminate any extra variables that might move things around. So you can see here, it was kind of thick though, and it also did not work. And it really was kind of clumpy in the center. So I decided to up the sulfur in the ratio. And I also lifted up the exit tubing clamp to try to push down the tubing that was actually inside the pump. And I switched out the pipe clamp by the nozzle because I had noticed some air. However, this also did not work because immediately when I poured through the sulfur concrete, it started to flow through just by gravity alone. So it started to solidify in this straight stretch here before I could even start with the pump. So I totally rearranged the system so that here you see it comes straight up out of the reservoir. So if this flows, it is because of the pump, but it was not strong enough to pull it all the way up. You can see it only made it about halfway up the reservoir. So I went back to the previous arrangement and I was able to actually extrude it finally. You can see here it came out, although the pan was too close. So almost immediately the system got clogged and that limited how much could come out. But this was still a really significant step. So this is the final stage, stage 5. It's when I attached it to the gantry system of SAMM and actually printed it along a 20-centimeter wall to allow it to actually build up with limited material. And you can see here it did start to actually layer up more so than it ever did last year. And you can see it's coming out really liquid, but keep in mind on Mars, it's a lot colder, so the solidification will be a lot faster. Also, this would be a lot bigger scale, and it's kind of irregular coming out. That's because this was done manually. I was holding the drill as opposed to the ultimate automated system that would be implemented. So you can see here, this is my coating. First off, it moved back and forth 4 times just to get it started, give me time to get into position to start everything. And then I had it move up so it could build up. And then I had another 4 laps just as a bit of a buffer to make sure all the sulfur concrete could be extruded. So in conclusion, a peristaltic pump is effective for extruding sulfur concrete. SAMM is able to build up with sulfur concrete, which I saw more this year in that wall than last year with that square, which is actually right here. Also, sulfur concrete can be reused, which is a really interesting aspect I discovered because a lot of times it would remain in that reservoir but not go into the system. So I just kind of salvaged it and reheated it. It took about the same amount of time to reheat. And this would not be an accidental thing because sulfur's melting point is 115 degrees Celsius, and that's a lot hotter than you're going to see normally on Earth, the Moon, or Mars. So limitations, I already mentioned the peristaltic pump was limited in its force. So with steep configurations like this one right here, or with thicker, more optimal ratios, it might not be able to force it through as this prototype. So longer term modifications would create a stronger system with thicker tubing, also motorized pumping instead of what I was doing with the drill, and also pump dependent flow, which is what I was trying to achieve here so that it doesn't start coming out and you have more control over the whole extrusion process. So something else that was really interesting that happened, I accidentally used a different simulant. It was slightly different. It was sent from previous NASA contact and it didn't work. You can see here, it did not cook sulfur concrete. This is the one I ended up actually using and had used in the past. So that suggests that optimal ratios, finding that is a lot more complicated and it might need to be determined per site. And also volume might be a better standardized measure of the optimal ratio than mass, which is what all the previous studies have looked at. However, volume is actually used a lot when making actual concrete on Earth. So there's a lot more potential for sulfur concrete on Mars that can still be researched, its strength, radiation shielding, and its durability. And there's a lot more that we can look into before we can actually build on Mars. Thank you.